Hi everyone, my name is Babak Badrzadeh. I'm currently an IEEE PES Distinguished Lecturer and working as a Technical Director with Aurecon Group in Australia. For today, what I'd like to discuss with you is to share with you some of the real-world operational challenges associated with planning and operation of inverter-based resources under low system strength conditions, and in particular as it relates to subsynchronous oscillations, which is the context of this panel session. And then I'll share with you some of the lessons we've learned. Before I start the presentation, I would like to thank session organizers for inviting me for this panel presentation. Also, my former colleagues at Australian Energy Market Operator or AEMO. Okay, let's set the context in terms of challenges associated with operating a power system under low system strength conditions. The left-hand side graph shows Australian national electricity market and compare its different areas in terms of available system strength, with the areas highlighted in red or pink represent those with the lowest available system strength. Unfortunately, as it occurs, this area attracts best available wind and solar resources, and most often they share two common challenges that they are typically very far from large and capable synchronous generators in the power system, and at the same time they are in close proximity of other inverter-based resources. For this presentation, we have chosen one particular area that is shown in the right-hand side graph that features both challenges that I mentioned in terms of sparsity and remoteness with respect to large synchronous generators, but also comprises very many different types of inverter-based resources. The key questions we would like to answer in this presentation is that how will power system instability manifest itself under low system strength conditions with growing share of inverter-based resources and declining share of synchronous generators in the power system? Are they consistent with known and familiar forms of power system stability, or are there new and emerging forms? And then what solutions are available to address these emerging challenges? And last but not the least, do all IBRs behave in the same way? Are there differences between different types of IBR? And if so, what causes those different behaviors? Okay, let's start with the classical form of subsynchronous control interaction, or SSCI, which is a relatively known phenomena. It has been there for 10 or 15 years and essentially relates to radial or near radial connection of a wind turbine generator or a wind farm against a series compensated AC line. It's typically associated with controls of type 3 wind turbine generators, and it has been documented in particular in Texas by ERCOT, and there are other presentations for today's panel session. Essentially, what would happen is that under radial or near radial connections, as soon as you switch in the capacitor, there would be some volatile dynamic responses associated with both the wind turbine and the series compensated line. In this particular instance, which is based on a published IEEE paper that I had personally around 10 years ago, the wind turbine essentially protects itself by disconnecting from the grid. And it's needless to say that the reason we are calling them subsynchronous interactions because the dominant frequency of oscillations is below the network fundamental frequency. What I'm going to discuss from the next slide is that what we had observed in Australia and how similar or dissimilar is with respect to this known form of SSCI. Okay, this slide shows more contemporary forms of SSCI as we had seen in Australian national electricity market. In this case, there is not any series compensated AC line nearby, But what prompts these sustained post-disturbance oscillations is the presence of multiple electrically closed IBRs when they are all operating under low system strength conditions. As we can see from the graph, without the IBR, there is no voltage oscillations. And as soon as the IBRs are connected, we see these sustained post-disturbance oscillations. The frequency of oscillations have been ranging between 5 and 15 Hz and were initially detected by wide area electromagnetic transient simulation, and subsequently AEMO were able to replicate these oscillations by stage simulation testing. One importance of this particular phenomena is that it is more difficult compared to subsynchronous control interaction involving a series compensated line to detect because IBRs in different parts of the network could interact with respect to each other, considering that the dominant frequency of oscillations is fairly low. I also note that this form of instability, as per the new IEEE TR77 publication, is classified as a converter-driven stability, which is a correct and precise term. Okay, in this slide, we take a look at various mitigation measures available, and then we'll discuss each in greater details in the next few slides. The first approach is the use of system constraints, which would either reduce the total output power of IBR or a cluster of IBRs, and in the most acute case, it would reduce the number of online inverters or turbines in the power system such that the post-disturbance voltage oscillations are brought to within the acceptable levels. The second mitigation measure is the use of nearby synchronous generators or synchronous condensers, and by having these synchronous machines, the available system strength to these inverter-based resources would increase, and it would mean that they would be able to resume their stability during and after the fault clearance, and the post-disturbance voltage oscillations would be significantly smaller. We can achieve the same performance also by inverter control system or parameter tuning, and whilst the available system strength is not increasing per se compared to the use of synchronous generators, but what the tuning means is that essentially the response of the turbine or inverter would improve under low system strength condition, even if that can be achieved by deprioritizing some other aspects of the response under low system strength conditions. And the last solution is the use of nearby grid forming inverters, which they would essentially achieve the same response that we could achieve with the real synchronous machines. Unfortunately, due to the confidentiality, I won't be able to discuss the details of grid forming inverters for this presentation, but I'm happy to take any questions if they come. Now, let's take a closer look at how the use of constraint will work. The blue color traces here shows the voltage oscillations, which is approximately 4% after the fault clears, and this level of oscillation is not obviously acceptable. Various forms of constraint were applied, including a reduction in the total megawatt that really wasn't helpful. And the only solution that were demonstrated successful is that not only to reduce the total output power, but also to reduce the number of online inverters. And as we can see here, once the total number of inverters were reduced to 35%, the post-disturbance voltage oscillations were practically removed. In this slide, we look at synchronous condensers as another option to address these subsynchronous oscillations. As we can see here, once we add one synchronous condensers, the level of post-disturbance voltage oscillations decrease quite substantially. And as soon as there are two synchronous condensers, the oscillations eliminate pretty much. In this particular instance, like I discussed earlier, with the synchronous condensers, the available system strength to IBR increases, and that would ensure that the original design and tuning of the control system for the IBR would still be relevant. And the third solution considered was the control system tuning of the inverters. As we can see from the graphs, with judicious control system tuning, the level of post-disturbance voltage oscillations reduces pretty much to the same level that we were able to achieve with two synchronous condensers, even though the synchronous characteristics or system strength in the power system is not enhanced. But what is happening here is that it would essentially make sure that the control system of inverters can still operate stably under this reduced system strength condition. Okay, in this slide, we're trying to convey another important message, which is the extension of what we discussed in the previous slide, that here what we're trying to discuss is that not only judicious control system tuning of grid following inverter based resources can reduce or eliminate their adverse impact on their low system strength conditions in terms of subsynchronous oscillations, but they could also help some other nearby inverter based resources in terms of suppressing those oscillations. What we are looking at in this graph is that we have a number of nearby grid following inverters, and when they all subject to the same fault that they would all observe due to geographical proximity, the level of post-disturbance oscillations is again unacceptable, as we can see from the black trace. And then we take out some of those grid following inverters, and as we can see in the red traces, the level of post-disturbance voltage oscillations would reduce as you would expect. Now, we are returning all these grid following inverters back to service, but the control system tuning of some of them is modified such that the impact on their low system strength conditions would improve. And as we can see in the green traces, is that the level of oscillation now reduces quite significantly, and that is even lower or significantly lower than that we can observe with some of the IBRs being removed. And that's a good success story, that essentially by improving the control system tuning of grid following inverters such that the weakness of the network to which they are connected is recognized, we can improve their stability impact. But this cannot be considered as a permanent solution. It is okay to the extent that the current level of inverter-based resources are connected to the power system. As more and more inverter-based resources would get connected to the system strength would decline, and at the same time, as more and more synchronous generators are withdrawn from the power system, and the destabilizing impact would also increase. And not only we need to have carefully designed grid following inverters in the power system, but we also need to consider what it takes in terms of synchronous machines or grid forming inverters that can at the same time boost the available system strength to the power system, such that these subsynchronous oscillations are mitigated or ideally eliminated. To summarize some of the lessons learned is that forms of system stability are not changing. We could classify these subsynchronous oscillations as converter-driven stability. The only difference is that as we are moving to a power system with much less of synchronous generators and increased uptake of inverter-based resources, the causes of the same forms of system stability are changing. And that without the use of wide area EMT modeling, and the prediction of these forms of system stability, especially as it covers a wide part of the power system, would not be possible. Also, what we learned is that grid following inverters are improving and their performance is evolving. And then we are also in parallel having grid forming inverters that collectively could help addressing many of the system stability challenges associated with increased penetration of inverter-based resources, and that we don't need to have a synchronous machine in the power system to address every single stability issue. This concludes my presentation. Thank you for your attention.